So far, we've learned several formulas for finding antiderivatives, but unfortunately, if our integral does not exactly match one of the formulas, then at this point, we don't know how to perform the integration. So in this section, we're going to learn a method for extending the number of functions that we can find antiderivatives for. It's a technique called substitution, often called U-substitution. Substitution. And it's a method basically of renaming variables. So here's an example. We want to find the antiderivative of e to the 3x. Now we have a formula for e to the x, but e to the 3x is not exactly the same as e to the x because there's a 3 in there. So what we're going to do to clean this up is we're going to give a new name to that inconvenient exponent. We're going to call it u. And it's standard to call these things u, that's why we call this u substitutions. With that renaming, what would du dx be? Well, du dx would be 3x. Oops, sorry, just 3. Now, let's start putting the u's into our integral. So I have e to the 3x dx. That's going to turn into e to the u because I've given the name u to 3x. Now I need to know what to put in for dx. So the trick here is to multiply both sides of this du dx expression by dx. And that will give us du equals 3dx. So what am I going to put in for dx? Well, let's solve this for dx. And I'll do that by dividing both sides by 3. And I see that 1/3 du would be equivalent to dx. So I'm going to put in 1/3 du for the dx. So I've now renamed everything in my integrand in terms of u. Let's get that 1/3 out of it. And now I do know how to find the antiderivative. The antiderivative for e to the u du would be e to the u, and then plus c. Now there's one other thing I have to do. Since u was just my name for 3x and not part of the original problem, I need to put back in that the exponent there is 3x. Integration is pretty tough. It's definitely harder than differentiation, but I do have some good news, and that is that you have the ability to check your answers using differentiation. So I'm claiming that 1/3 e to the 3x plus c is an antiderivative for e to the 3x. Remember, if you differentiate the antiderivative, you get back to the original function. So let's do that. I'll have 1/3, and then I'll have e to the 3x. I have to multiply by the derivative of the 3x. That's because of the chain rule. And then the derivative of the constant c is just a 0. The 3's cancel and leave me e to the 3x, which is the function I was trying to find the antiderivative for. Let's see another example of doing this. I'd like to get the antiderivative for 10x minus 2 over 5x squared minus 2x plus 3. We know what to do if we're adding or subtracting inside the integral. That we can just break up our integral with pluses and minuses. But there's no rule for, and maybe I should even write that in here, there's no rule for if I'm dividing two functions in there. And there's also no rule for if I'm multiplying two functions in there. Okay, so in example 2, I'm dividing two functions. I don't have a rule for that. We are going to let u be the denominator. So I'm going to give the entire denominator the name u. And don't worry how I decided to let u be the denominator instead of the numerator. We'll talk in a little bit about some ways to decide what u will probably work for you. So then du dx would be 10x minus 2, and then we always want to multiply both sides by dx. Oh, and look, 10x minus 2 times dx is actually right there in the integrand. So this is going to turn into 1 over u du. So the 10x minus 2 dx, that's all swallowed up inside the du. Now I know how to integrate it. The antiderivative for 1 over u du is ln of the absolute value of u plus c. And last step is to put our x's in. So 5x squared minus 2x plus 3 goes inside the absolute value bars.